Welcome everyone. Today's talk is about mathematical modeling of the evolution of human post-menopausal longevity. Our speaker is Miss Anthia Lee from the University of Queensland.
Thank you, Liam, for that lovely introduction. I feel like I should apologize. I'm a little bit sick, so hopefully you guys will still like my presentation. So hi, I am going to be talking about mathematical modeling of the evolution of human post-menopausal longevity. So oh, so I'm going to just go through a model seen in this paper that I wrote with Peter Kim. So if you want to follow through, then please scan the QR code at the bottom. And if I have time, I'm going to lightly touch on the second model that's in this paper. So through Darwin's theory of evolution, we know that we share a common ancestor with the great apes. And so what does this mean? It means that we have the same female fertile lifespan as like other great apes like chimpanzees. But because our evolution focuses on cell repair, it means that we actually have a longer somatic lifespan than like chimpanzees. And so this means that human females have a postmenopausal, can live to experience the postmenopausal period, unlike chimps. So then the big question is, in this era is, how did menopause evolve in human females? Well, in 2013, Morton et al. Tried to address this problem through their paper, Mate Choice and the Origin of Menopause, and they published this in PLOS. And so in this paper, they hypothesized that menopause is a consequence of male mating choices. And using an agent-based model, they concluded that a higher preference towards younger females leads to the evolution of shortened female fertility at old age. And oh my goodness, this caused such a stir, not only among academic circles, but also amongst the general public as well. So the BBC picked this up and queried, amend blame for menopause. Yikes. And it really does not end there. So Andrea Saani in referenced their work in her book Inferior, How Science Got Women Wrong. And in this, she basically went and interviewed a bunch of academics doing research in this particular area and asked them what they thought about Morton et al.'s model. So this is a snippet from one person called Rebecca Sears, and just reading the first line, she said, "It's a stupid argument. It was trash when it came out. It's a circular explanation." And it's true that it's a circular explanation, but their model was not trashed. Like, this is when mathematical modeling is so important, because there aren't very many models done in this area. People are still building upon Morton et al.'s model to this day. And during my PhD, I basically, for the start of it, at least concentrated on making ODE models that is analogous to Morton et al.'s agent-based model to sort of verify their conclusion. However, you don't have to wait until you are in like master's or PhD to be able to do this. Students can do simple like ODE models to investigate this problem using techniques that they're learning in undergrad courses. So I'm just going to take you through one of the simple models. So in the paper that I wrote with Peter Kim, we showed like a female only model where we're just varying fertility. And so what we're looking at is under what conditions old age infertility can become dominant. So we're focusing on just something simple, two populations. On the left-hand side, we have females with lifelong fertility, which means they can reproduce for the entirety of their lifespan. And on the right-hand side, we have a population of females with old age infertility, which means that they will stop reproducing at a certain age, like middle age, 45. So let's draw this out. We have one box representing F1 females and one box representing F2 females. And they're just going to die. So we're going to have a death box. And so let's just start drawing the connections with this system. So the easiest one to tackle is death. F1 can die at a death rate delta, and F2 dies at a death rate delta as well. So I'm assuming same death rate. But then what happens with the transition between F1 and F2? Well, Morton assumed a deleterious mutation, which means that F1 females can produce offspring with offspring who can have the trait 2, so they can have old age infertility. But F2 females cannot produce an offspring that has the F1 lifelong fertility trait. So the arrow just goes from one direction. And how do we explain this mathematically? So I'm assuming that there is epsilon probability of producing an offspring with the deleterious mutation. But then we have to work out who can produce these offspring. So going back to the comic, in this we have a young female and an old female. So now I'm going to sort of assign a breeding rate for these females. So the young will have a breeding rate of A, and the old will have a breeding rate B. But the thing is that I'm assuming that young females, it's easy for them to find a mate, but for the older females, they can only have a probability gamma of finding a mate. So let's put this all together. The connecting line for the deleterious mutation is epsilon A plus gamma B. And so now we're just going to look at where there is no mutation. So each mother from this F1 and F2 female population will have offspring that has the same trait as them. So similar to before, I'm just concentrating on the F1 box. I'm going to assign a probability of them being able to produce an offspring with the same trait. So that's 1 minus epsilon. And like before, I need to kind of say like who is going to produce these offspring. So it's going to be the same A plus gamma B. But for F2 females, it's going to be slightly different. So we're just going to concentrate on that arrow now. So we kind of we know that they're not going to actually have a chance of mutating, like having the F1 trait. So there's not going to be an epsilon or probability of mutation there, but they're going to have a breeding rate. So in this one, the older females can't reproduce, so they don't have a breeding rate, but it's for the young females. So it's only A. So, whoops. Yeah. So, yeah, that's what it has. So now when you try to write the equation, so we're just going to focus on like who will stay or who will join. the F1 population. So I'm just going to remove all of the lines that we don't really need so that it's easy to see. So the only way to contribute to F1 is through F1 mothers producing offspring with the same trait as they do. And then they will die at some death rate. So then the equation is just derivative F1 is equal to 1 minus epsilon A plus gamma B multiplied by F1. Is coming from F1 minus the death. And for F2, this is a little bit harder, but we're asking the same question. Who will stay and who will join F2? Well, let's remove all of the lines that aren't needed. So we know that the people that would join F2 are the offsprings produced by F1 who has the number 2 trait, and the offspring that are produced by F2. And they also die at some death rate. So the equation is now derivative F2 is equal to epsilon A plus gamma B F1 plus A F2 minus delta F2. So here's the two equations side by side. And I'm sort of just gonna quickly segue a little bit to just the parameters for anyone who's interested. Because we don't actually have a time machine to go back in time and, you know, collect data from our ancestors, we're gonna use the next best thing, which is survival data from the remaining hunter-gatherer societies, the Hasda. And so we just sort of plot their like survival data. And basically, this is when MATLAB is your best friend, and you can numerically integrate to get proportions of young, old, and death rate. And you can find these values in the paper if you are interested, like if you like, or you can simulate it, which I think there is a thing to the data itself as well. So back to the model itself, how can we analyze this model? So there are two ways that I present. It's the explicit solution, or we can transform the system into a 1D ODE. So So for the explicit solution, we can write the model in matrix form. And it's basically just a linear system of two equations. And in Australia, around like end of first year, start of second year, students will recognize that we can solve this by using eigenvalues and eigenvectors. So given the eigenvalues and vectors, students can check the solution, but I feel like the biggest thing that we could concentrate on is actually explaining, like connecting the maths, like, and what is happening with this real life problem. So I think it's really good if students actually write in words what is happening. So what is happening in the long term? Well, back to the F1 and F2 populations. If Lander 1 is less than Lander 2, then we see that F2 dominates and F1 just goes extinct. So in that case, old age infertility can thrive. But when Lander 1 is greater than Lander 2, then we kind of see that there is coexistence with the two populations. So yeah. And the second way that we can kind of analyze this system is that because we're just interested in the traits, then we can rewrite the equation in terms of the proportion of each trait in the total population. So let it T be the total population equals to F1 plus F2. And, and so to rewrite in terms of trait 1 and trait 2, we're gonna call it U1 is equal to F1 females out of the total population, and U2 is equal to F2 females out of the total population. And using quotient rule, which I think people should know from high school, we can rewrite this as the derivative U1 is equal to 1 over t multiplied by the derivative f1 minus f1 on t squared multiplied by the derivative of the total population. And I feel like at this point, students will look at this and be like, wow, that is a monstrosity. But I think the good thing about working with proportions is that we know that U1 plus U2 is equal to 1. So it means that we can basically write this in terms of U1 alone by just letting U2 equal to 1 minus U1. And so we substitute everything in and we can find simplifications. And an easier thing to do as well is to let U equal to U1. And so we get this nicer equation at the bottom of the screen to work with. So then what actually happens in the long term? So we can find the critical points. So derivative equals 0, and we solve for U. So we have two critical points, U equals 0 and U equals to 1 minus epsilon 1 plus A over gamma B. So we can actually look at determining the stability of this system by just plotting the growth curves. So we have two parabolas here. So let's kind of look at each one. So the one on the left-hand side, we see that when the critical point is 0, it's unstable because it is at an upwards slope. And the other critical point is on a downward slope, so it is stable. But then what does this mean to the actual population itself? Well, it means that long-term, lifelong fertility will be the dominant trait within the population. Now, on the other hand, with the critical point being smaller than 0, it is unstable. And when the critical point is, well, because it's like in an upwards slope. And when the critical point is 0 on a downward slope, it is stable. So what does this mean? It means that as time through long term, lifelong fertility just won't be dominant at all. So we see that the epsilon 1 plus A divided by B is kind of like this turning point in the system. So what else can we do? So we can plot this bifurcation plot, and we can see that it's a transcritical bifurcation. But what does this mean again? Because like it's nice, but let's connect it to the problem. So I basically just substituted the values in, which again, you can get from the paper, just substituting for A and B, and I'm solving for like gamma. So gamma, if you remember, is the probability an older female finds a mate. And what you find is that even if this probability is really, really small, F1 females can just easily dominate the population. So this means that F2 can only win when older F1 females can't find a mate. So we can already see that there are some issues that were overlooked in Morton et al.'s agent-based model, that this simple model has started to pick up. But I feel like a lot of people will start asking questions like, hey, that's only a female model. Maybe the dynamics will change when you start including males. And I'm just gonna quickly touch on this, but you can basically add in males by having males vary in mating preference. And so you introduce two populations of male. The one on the left-hand side will be the fussy males who will only mate with young females. And the one on the right will be the unfussy males. And they don't discriminate. They're going to mate with females regardless of age. It could be young or old, just above the juvenile age, basically. And you can go through a similar process that I literally took everybody through for the female only situation. So you draw it out, you write the ODEs, and you can basically use the same transformation, but rather than turning into a 1D, it's like a 2D equation. But just to quickly summarize the results, we can see that our ODE-based model shows that male mating choices can lead to the evolution of menopause, but it's only under the most stringent condition. Virtually all males must be fussy and can only mate with young females. So we found that even if a small number of unfussy males are present, then menopause just won't evolve. And this is a really unrealistic scenario because how can we expect all males to collectively only mate with young females when they're actually trying to compete for paternities? So I guess that's just a very interesting way that students can already start addressing like these big problems. And you can find out the bigger model if you are interested in our paper. It's a collaboration between Kristen Hawkes and Peter Kim here, and you can scan the QR code if you like. Yeah, but thank you so much for watching, and I hope you enjoyed the presentation.